So do some examples with binomials, but first we got to establish that this is a binomial. So we have children. Genetics says that the children receive genes from each of their parents independently. Remind me and I'll tell you an interesting story of when I had my daughter and how my knowledge of blood types helped me out at the hospital with my mother. Anyway, if these parents have 5 children, we're going to have X is going to be the count of children with type O blood. Okay, so we've defined what X is. Now let's see if this meets the binomial setting. It does say that it is, but let's just prove it. B. Success is equal to type O. Failure equals not type O. Type O. Independent. We do know that with these children, each one is going to have the same probability of getting type O or not getting type O. So each child blood type is independent. You could also use the 10% rule for this. N, how many children are we having? We are having a fixed number of trials of how many children? It says children, 5 children. Okay. So that is a fixed number of trials. S, now we write out what the probability of success, and if we are indeed independent, it's not changing each time. They have the probability of a quarter, which is 0.25, and 0.75 for failure. Okay, so let's create a probability distribution in our calculator. And so, got my calculator here. All right, calculator. All right, have some old data there, so I'm going to clear that. This one I actually have not entered yet. Okay, so first of all, whenever you have a binomial, you have to remember that you start at 0 for your X list. And I'm going up to 5. Now for my L2 list, as we said in the formulas thing, I've got to go up to the top. Now I'm going into distribution, where I will find the binom PDF and CDF formulas. They are down here at, my calculator has them as A and B, so they're kind of a little ways down there. Now I have 5 trials. Success is 0.25. I'm going to leave that blank because I want it to autofill. And I say paste. There's the formula without an X. It's going to go in and enter it autofill. So those are the probabilities. I can now put that table on my note packet. I have made the table of these values, and we're going to use this to find mean. We can use this also to find the mean and standard deviation. I think I'll just do that right now. 1 var stats, L1, L2. If you don't need your L2 for something, make sure you get rid of it, but I need it. And so my mean is a 1.25. There's no sample standard deviation because this was a probability distribution, a special one called a binomial. There's the standard deviation. And then if I needed it, I have my quartile information. And I could always graph this as a box plot and a histogram, but I'm not going to do that. So I've got my mean, I've got my standard deviation, and let's put this probability distribution that I created on my calculator, and because of the way my paper is, I think I will orient this thing horizontally. Okay, 0. And if you have something in scientific notation, let's just leave it in scientific notation, okay? Keep it simple, people. I don't know who keeps making you change your scientific notation to non-scientific, but it's actually quite useful to write things in scientific notation. So highly unlikely to be 5 babies with O blood. Okay, so now find the mean and the standard deviation. There were 2 methods for doing this. We just did one by doing 1 var stat using the L1 and the L2 list. We found that the mean was, now I don't remember what it was, 1.25 children, and the standard deviation was 0.968 children. But there's also, from the formula sheet, there are the formulas. And especially if you have a very long list, you might not want to use a calculator. If you had, say, you had 100 trials, are you going to sit there and type 0 to 100? No. So n times p, and the standard deviation is going to be the square root of n times p times q. The variance would have been the n times p times q, but so let's just plug this in. We have 5 trials, we have 0.25, and that confirms that we have that many children. And if I plug in 5 times 0.25 times 0.75, let me extend my square root so it covers it, and that comes out to be 0.968 children. So very nice to be able, once you've established that something's a binomial, you can do a lot with it. Okay, so now what's the probability of exactly 2 children having type O blood? And I can actually see it on my table, which I have in my calculator. This is exactly 2 right there. So let's write out the formula from the formula sheet. So the probability that x is going to equal exactly 2 from the formula sheet, I'm going to write, there are n trials, I want exactly 2, 0.25, that was the probability of success, and I want there to be 2 of those, and then 0.75, and I want there to be 3 of those failures. And then that probability from my list right there. And then I would say the probability of exactly 2 children having type O blood is 0.2637. Or estimated to be. Let me make this a little longer. Is estimated to be 0.2637. And nobody said that I am the neatest writer. Okay. So that's exactly 2 right off my table. Okay, but now we want at least 4 children have type O blood. So what does that mean? At least, if I tell you you need to bring at least $4, you could bring more than that. So this is going to be the probability that my x is greater than or equal to 4. So that means that I am going to have to take my probability of 4, and I'm going to have to add that to my probability of 5. 5. And I do have both those numbers on the table. And I can get those numbers from the table. I'm also going to show you how I could put in the cumulative probabilities just to look at that too. But I'm going to write out the formula with the work. So I have 5, I want 4 of them, 0.25, 4 kids are successes, 1 child is not a success, and I'm adding that to 5 children, 5 choose 5, 0.25, there's going to be 5 children like that. I like to put parentheses, but it's not totally necessary. There's none like that. Of course, that 0.75 to 0 will be 1. And 5 over the 5 combinations, that's going to be 1 as well. But anyway, and then this on our calculator, when we add it up, I'm just going to write the answer. I've added the 2 categories. I just want to show you how I might have done this using the CDF. If I wanted to use binomial, which I would never write calculator speak on the paper, if I wanted to do that, if I did 5, 0.25, 3, if I got that number, that would be the probability of my x being less than or equal to 3, which is less than 4. If I got that, the complement of that would be being greater than 4. So let me just show you with the calculator, how I might use that number. Because here's my same calculator. Okay, going into here, like if I put the CDF in this L3 for a second here, so again, it's under distribution, same place as normal CDF and inverse normal, but I'm going to scroll all the way down to binomial PDF, or binomial CDF this time. And I'm going to leave the X off again because I'm going to just show you how I could fill in the whole table. Leaving the X off because I'm filling in a table. So you can see that that's 0. That's 1, 0 and 1. That's 0, 1, 2. 0, 1, 3. And so if this is 4 and less, this is 5 and less, and of course it would equal that total thing. So if I go 1 minus 0.9844, I end up with the same value of 0.0156 that I just found by the adding of these 2 categories. Those 2 added up is that. These 4 added up right there, 1 minus that. So you can use whatever method's making it easier for you to do. So I'll just write down these numbers that, because like this number was 9844, and so the probability that my x is greater than or equal to 4 is going to be equal to 1 minus 0.9844, which is 0.0156. Okay, so the probability of that at least 4 children have type O blood is estimated to be 0.0156. That's 3 significant digits because the leading 0 is not significant. What's the probability that 4 children have type O blood? Okay, so when it's worded in this way, it's actually saying 4 or more. Because if you think about it, if you have 5 children of type O, then you have 4 plus a spare. Okay, so it's going to be important if they say exactly 4, then they mean exactly 4. But if they say 4 children, that actually is really saying at least 4 children. So we actually have that probability. We just found it right above, and it is 0.0156. So it was the same as what we just found. So should a parent, now that we've got this result, should a parent be surprised if more than 3, probability X is greater than 3? That is the probability that you're greater than or equal to 4. If they have more than 3 of their children have type O blood, should they be surprised? So remember that when you're justifying your answer, you need to use numbers. And when you're making a comparison and a conclusion, you need to have the numbers to support it. So since the probability of having more than 3 with type O blood is estimated to be 0.0156, which is, now I'm going to make a comparison, which is less than, what should I compare it to? 0.05. Okay, so what's that mean? If it's less than that, then it is unusual and they should be surprised. That's what I would say. So notice I had a number I compared it to. I had mentioned everything that I was talking about in this problem, being the type O blood, being the, might want to add in there out of 5 children. Just to like make sure they really know what you're talking about. Okay, so what's nice about these binomials is that if you can prove the BINS is met, even if it's just met enough, as in like the 10% condition for independence, if we can prove that it's met enough, then we can do a binomial. So let's solve this problem, which is not really a true binomial, but it's binomial enough because the independence is met enough. And so this is my favorite check for independence right here because it works for finite groups. So we have this simple random sample, and let's go through we have these CDs. They have defective copy protection schemes that can harm your computer. And so they've inspected a simple random sample of 15 CDs from a shipment of 10,000 CDs. This number is actually important to help us do this right here. Let X equal the number of defective CDs. So that's nice. They've already defined that for us. What is P of X equals 0? So B. Success here, bad CD. Failure, not bad, or good CD. Independent. Well, it's not truly independent because we have no replacement, but is n less than or equal to, let me just write the word independent first. I like to keep things Okay, is n less than or equal to 10% n? Since 15 is less than or equal to 10% of 10,000, you just need it to be over 150. Therefore, that's the symbol for therefore, it is independent enough. Okay, now let's do our n. Can we have a fixed number of trials? Yes, we have n equals 15. That was a simple random sample. And p, the probability of success, is 12% were bad. So just double check that when you're writing your p, it has to be for the thing that you have said success is. And so that makes my q equal to 0.88. Okay, so that's all set. Let's go in here. We want no bad CDs, so we want the probability that my x is equal to 0. I'm going to get this. I'm writing it over here in red. I'm going to use binomial PDF. I'm going to put in 15. I'm going to put in comma 0.12, and then since I want exactly this one thing, I will put in the 0. It'll spit out a number, but I will not write that on my test. If you did write this on the test, you would want to make sure you've defined every one of the little pieces, so that they probably wouldn't mark you off if you had defined the individual pieces, but if you don't define them, they will mark you off. So now let's see, we've got 15 and we want 0. We want none of them to be good probability. We want all of them to be the bad. And that comes out, if I plug it in the calculator, using binomial PDF, 0.147. So, yeah. And 15 choose 0, that does come out to be 1. And 0.12 raised to the 0 also is 1. So really, this is 0.88 to the 15, but it doesn't really matter. So then the context is the probability of no bad or defective CDs in an SRS of 15 CDs is estimated to be 0.147. So showing you that you can use the binomial and have that independence check. And that independence check is also necessary if you're going to use what's called the normal approximation for binomials. This approximation is our best friend when we get into some later chapters, but in order to use it, we need to establish that something's nearly normal. And basically what happens is as you increase your sample size, you can see at a sample size of 10, we have a little bit of a tail here on the left side, so a little bit of a left skew. But as you increase the sample size, this tail decreases until it's basically nearly normal. But how big does your sample size need to be in order to make this nearly normal approximation happen? Well, it needs n times p greater than or equal to 10 and n times q greater than or equal to 10. See how amazingly awesome these large things are. And then you'll have your mean and your standard deviation, and that's basically, you know, what you have to know for your curve in order to make this thing, you know, work. So on the next page, I'll do an example. I'll do it with a binomial and I'll do it with a normal approximation, and both methods would be perfect on the AP test, but they both require you to establish your conditions. So we have this sample survey. Fewer people are enjoying shopping than in the past. The survey asked a nationwide random sample of 2,500 adults if they agreed or disagreed. So that's a binary thing. Do you like buying new clothes or not? So let's just first define our success. Will be that we like buying, like shopping, and failure, well, we don't like it. So I guess in a way, this is yes, and this is the no's. Okay, independent. Are we going to be able to establish independence? The sample is 2,500 adults. Don't fall into the idea that like one adult is not going to affect the other adult, because that is not the appropriate independence check for this. This is called a finite situation. There are a certain number of adults out there that like shopping, and there's a certain amount that don't. And once you've picked one of these people, your samples, your population size, you have less for the next person getting picked. So this actually, to do independence here, we really do need to establish it using the 10, n is less than or equal to 10% n. And we can do that because 2,500 less than or equal to 10% n. There are more than 25,000 U.S. adults, right? I think this was U.S. adults. I don't know. Okay, and do we have a fixed number of trials? Yes, we just established. Here's our n, our little n, and our probability of success is, now that we were able to approximately have independence, we can keep this probability of success of 0.6. Make sure you're checking that it really is the yes group, and Q will be 0.40. So we want the probability that 1,520 or more agree with this. Now, I am not going to write the work from the formula sheet for this because that is so many. So this is a situation where I really will use my norm CDF, my binom CDF, and what I'm going to do is I'm going to say 1 minus the probability that x is less than 1520. And I'm just going to write right below it probability x less than or equal to 1519, because that's what I actually would have put into the calculator with that. To get that, I would have used binom CDF, where my n was equal to, well, I guess if I was writing it out this way, but just so you know what I would have put into the calculator, 2,500, comma 0.6, comma 1519. Let's find out what that number is. Do that on the calculator. Okay. So for my work's just going to be the stuff that I have in blue. So, oops. I'm just trying to cover up those numbers, but why? I don't know why I bother. Okay, so again, the distributions, which is at vars, where we find our normal CDF and inverse normal, but scrolling way down, this time to binom CDF, 2,500 people, 0.6 is the probability, 1519, and that's going to add up. For the binomials, it's going to be the cumulative amount all the way up to 1,519. So it's adding 0, 1, 2, all of those. There's my probability. 1 minus this answer, and that's the probability of being above that. So being a 1520 or higher. So, okay, so I didn't write the red stuff on my paper, but I am writing the blue stuff on my paper, and so there's not really a lot of work that I'm writing. And okay, and so then let's call this 0.213. And so that's using the binomial, and then of course I would have my context. Now I want to just illustrate how we can approximate this with the nearly normal approximation, and let's see how close we get to that value. So nearly normal, we need to be random, and that was given an SRS, simple random sample. I need to be independent. It's actually the exact same check as what I did for the one above. I have 2,500 is less than or equal to 10% n, since more than 25,000 adults. Okay, now I need to be nearly normal. And the check for that, when we have probabilities like this, I need my n times p needs to be greater than or equal to 10, and my n times q needs to be greater than or equal to 10. N 2500.6. Okay, 0.6 times, okay, 1,500 is greater than or equal to 10. And if I had checked the Q first, really, then I'd know that it was going to be greater than, because 40% of it is going to be a lower number. But anyway, so we've established our conditions. That means that because we've established that it's nearly normal, we can in fact draw our curve. Okay, so the middle of this curve is going to be that n times p, which is right here. So that is the middle of our curve, but our standard deviation will be the square root of n times p times q. So 2,500 times 0.6 times 0.4. And so my standard deviation, take the square root of that. It's, let's see, square root of 600. So that is 24.4949 repeating, but whatever. Anyway, we want the probability of x being greater than or equal to 1520. Now I could just do it like that. I'm going to show you a way to get even closer with this approximation, but let's just go with the 1520. So I'll go with the z is going to be 1520 minus the mean over the standard deviation. I get, I don't know what I get, but whatever it is, then I could find the probability of being, well, I guess I'll punch it in. Okay, this one here comes out as 0.207. That's slightly off of the 0.213, but it's really close enough in statistical terms. But if I wanted to get even closer to that, I could redo this because these are binomial things. If I split that 19 and that 20, and so if I use 1519.5, I actually will get a much better value. So I could do my z-score with that, and it will come really, really, really close to this. And so this comes out to be 0.21299. So as you can see with rounding, that really is spot on at that 0.213. So in doing this binomial approximation, you may or may not remember this, but it's not really that important. This number was good enough. And the fact that I say estimated when I put my answer in context, that's why I can be slightly off like that.